And the next topic in this chapter is related to the specific heat capacity. And we also have calculation part in a specific heat capacity. So if we start with specific heat capacity, so before writing the definition of a specific heat capacity, if we talk about some common example of our daily life, just like if we talk about the boiling of water and if we talk about the heating effect of a spoon, let's suppose if we are talking about a spoon which is placed in a hot water and the water which is boiling and we are providing thermal energy. So what is the difference between the boiling of water and the temperature increase of the spoon which is placed in a hot water, or let's suppose is placed in a coffee or in a tea? So what do you think that what is the difference in the heating effect or the absorption of heat in the both case if we talk about the boiling of water and the temperature increase of that spoon which is kept in the coffee or in the tea?
The temperature of the spoon will be warmer.
Yes, the temperature of the spoon will be greater or warmer as compared to the temperature of liquid. So to find out the reason or to find out the actual difference that how we compare the temperature between these objects or between these different states of matter, so we have to find out the specific heat capacity. Specific heat capacity is basically a quantity or a specific quantity of a heat. Let's suppose if we have three materials, solid, liquid, or gas. If we are working with three different matters, solid, liquid, and gas, and we are taking equal part of each matter, we are taking equal solid, equal amount of liquid, equal amount of gas. So if we provide thermal energy or if we start heating all these states of matter, so which state will get more warmer as compared to the other?
Solid?
Solid. So the temperature of the solid will increase more as compared to the temperature of liquid and gas. So the reason behind it, or if we want to explain, or if we want to uh, find out the reason with the concept of a specific heat capacity. So basically, specific heat capacity tell us about the amount of heat, the amount of thermal energy or heat. We can say both of term are suitable for writing the definition. So we are writing the amount of thermal energy required to raise the temperature of a body, temperature of a body to 1 degree Celsius or 1 degree Kelvin. So let's suppose if we are talking about the amount of thermal energy or amount of heat which is required to raise the temperature. Let's suppose if we are talking about solid, liquid, and gas, and initially they have their initial temperature, let's suppose 25 degrees Celsius, 18 degrees Celsius, 17 degrees Celsius. So these are their initial temperature, right? And if we want to increase their temperature by 1 degree, let's suppose we want to increase 25 to 26, 18 to 19, 17 to 18. So how much heat or how much thermal energy is required to change their temperature by 1 degree? So that concept is known as specific heat capacity, right?
Okay.
So that's why we are using word specific, and heat capacity means that amount of thermal energy or amount of heat that is going to be stored by the matter, right? So normally if we talk about solids, so the specific heat capacity for solid is low, right? Because the temperature of solid will increase uh, more as compared to the liquid or gas. But if we talk about liquid, so the temperature of liquid will rise in more time as compared to solid. So the process of rising temperature in liquid is less as compared to solid. And if we talk about gases, so gases or the process for gas is also slow as compared to liquid and solid, right? We will also discuss some examples with the values that what are the values of some common examples that we use in our daily life, just like water, iron, copper, steel. But before that, if we talk about the symbol, so the symbol for specific heat capacity is equals to C. So C is the symbol for specific heat capacity, and the formula for specific heat capacity is equals to, so if we talk about the formula, so formula is equals to C is equals to, if we continue or if we take the reference from definition, so the amount of thermal energy. So amount of thermal energy means amount of energy, delta E, right? Divided by required to raise the temperature of a body. So it means we also have some mass of a body over here. So small m, mass of a body, and we are going to raise the temperature by 1 degree. So it means for temperature, we are using delta theta. So m represents the mass of a body, C represents the specific heat, E represents the amount of energy, or you can simply say that the amount of heat energy, and delta theta represents you the change in temperature, right? Okay.
And yeah,
And if you want to write the SI unit, so what will be the SI unit according to the formula?
joules per something?
Yes, you need to just find out the individual unit, so that will land you to the final SI unit of the specific heat capacity. So if we talk about the SI unit, so SI unit is also very simple for specific heat capacity, and that will be equal to joules for energy, kg for mass, joules per kg. And if we are using Celsius scale, so per degree Celsius, or if we are using the Kelvin scale, so joules per kg per Kelvin, right? So it depends upon the temperature scale that on which scale we are working on, right? So joules per kg per Kelvin or joules per kg per Celsius. So these are the temperature of, sorry, these are the SI unit of the specific heat capacity, right?
Yes.
So any confusion?
No.
Okay. And if we talk about, or if we want to compare the thermal, sorry, specific heat capacity, so if we compare the properties of solid, liquid, and gas with the reference of specific heat capacity, so specific heat capacity of solid is less than the liquid. So it means that the we require less amount of heat because the specific heat capacity of solid is less than liquid means we require less amount of heat to increase the temperature of solid, right?
Yeah.
And second, if we talk about the specific heat of liquid, so specific heat capacity of liquid is greater than the solid. And let's suppose if we compare the value of water, so if we take the example of a water, so the specific heat of water is 4200 joules per kg per Kelvin. Okay, so this is a calculated value of a specific heat of water. So you can easily compare that how much amount of heat we require to increase the temperature of a liquid, right? That scale is for Kelvin. Sorry, this is for Celsius, 4200, right? So it means the specific heat of liquids are in thousands. And if we talk about solids, so the values of solids are around in hundreds or in tens. So because they easily conduct heat and the temperature of the solid will increase very quickly as compared to the liquid or gas, right?
Yeah.
Okay. So this is another concept of a specific heat capacity. And if you want to solve a simple question just to practice the formula, so let's suppose we have a question over here. So if 20,000 joules is supplied to a mass of 5 kg and its temperature is or temperature rises from 15 degrees Celsius to 25 degrees Celsius, calculate the specific heat capacity of the mass. Okay, so you need to find out the specific heat capacity of the mass, and we have some values given over here. So we need to find out the value of specific heat capacity. So what will be the value of specific heat capacity?
40,000?
40,000. Okay. So according to the formula, we have amount of energy of over here. Formula is C is equals to delta E over M delta theta. So we are having a value of energy that is 20,000 divided by the mass that is equals to 5. And there is a temperature change. So for temperature change, we need to minus the values or to subtract the values. That is 25 minus 15. It means it will be equal to 50.
Oh, it's 400.
Okay. So now we are getting answer 400 and the unit joules per kg per degree Celsius, because in question, the values are given in degree Celsius, right?
Yes.
So now we have another formula. Previously in this chapter, we don't have any formula. In previous chapter, we are having with one formula, that is P1V1 equals to P2V2 for Boyle's law. And in this chapter, we are having our first formula, which is related to specific heat capacity, right?
Yes.
Okay. Further, if we talk about some other process, because initially we talk about the thermal expansion and the other processes in this chapter or in thermal physics, we are having melting, boiling, and evaporation. These are some common process which you already know about it and already studied in your chemistry subject. But we have to discuss about some important factor and some similarities and some difference between these process, because you already know the basic concept. So we are not going to discuss about their basic definitions. You already know about it. So we just, let's suppose if we start with the melting process. So melting process takes place for,
Solids.
yes, normally we are talking about solids. So when we try to convert or when we try to change the state of matter from solid to liquid. So if we provide some thermal energy to solid, so it will convert into liquid. So that process is known as melting, right? And further,
Yes.
if we talk about the boiling process. So boiling process is normally for liquid.
Liquids.
Yes, it will be for liquid to the gaseous state, right? And if we talk about evaporation, so evaporation is also for liquid to gaseous state, but the difference between boiling and evaporation is that we provide some thermal energy in boiling, right? But in evaporation, we are just going to convert liquid into gas uh, in room temperature or in the normal temperature, right? We are not going to provide external thermal energy, right? So it means we are not working with external thermal energy. We are just working with normal temperature, right? So that is the difference between boiling and evaporation. And that is also very important in your syllabus and in this chapter, that what is the difference between boiling and evaporation and what are the factors on which evaporation depends. So boiling and evaporation is also very important because melting is something different. So we will discuss melting process individually. But first, let's talk about the difference between boiling and evaporation, right? So if we talk about boiling, and if you know about the boiling point, uh, which is related to the liquid, and if we talk about the boiling point of water, so what is the boiling point for water?
100 degrees.
100 degrees Celsius, right? So it means for boiling, we require some specific temperature, right? Or definite temperature. So that temperature is known as boiling temperature, and the whole process is known as the boiling process, right? So normally, boiling occurs at a definite temperature, because they ask you about to write the difference between boiling and evaporation. So that's why this concept is important. So boiling occurs at a definite temperature. So it means we require some specific amount of heat and some specific temperature to convert the liquid state into gaseous state, right? And if we talk about the evaporation, so basically evaporation takes place at the atmospheric temperature or at normal temperature, let's suppose. if we hang some cloth on the wire to let them dry, so we are not providing some thermal energy to dry those clothes, but due to the speed of the wind and the temperature of the surrounding and due to the open surface area, these are some factors which start moving the high energy particles or the high energy molecules of water from that surface to the atmosphere, right? So the high energy molecules on the layer of that solid material, let's suppose if we take the example of a wet towel. So if we are hanging that towel on the wire or on some pole in daytime, so due to the thermal energy which we are encountering in our daily life or in our atmosphere, so with the help of those energy, so the molecules or the water molecules on the top of the surface will get some energy and start moving away from that surface, right? They are going to leave the surface of tall and they are going to add up into the atmosphere in the gaseous state, right?
Yes.
So that is the concept of evaporation. We don't require a specific temperature. So that's why evaporation can be happen at any temperature because the molecule requires some amount of energy, and by getting those energy they can easily escape the surface of that solid and add up into the atmosphere. So only few particles or molecules evaporate in the atmosphere. So only few energetic particles or molecules. Let's suppose if you keep the bowl of water in a sunny day, so it will automatically evaporate, right? Because of the temperature, because of the open area, because of the speed of wind. So that is the process of evaporation. We are not providing some external source of heat. So few energetic particles close to the surface of liquid may escape and become gas particles, right? So this is the process of evaporation, right? And most important thing, it occurs at all temperature. We don't require any specific temperature to evaporate liquid molecules, right? Any confusion?
No.
Okay. Now, further, if we talk about the factor affecting evaporation, so we are going to talk about the factors which affect the evaporation process. Or let's suppose if we are going to discuss that how the evaporation process will increase or decrease. So the first factor is that if you want to increase the rate of evaporation, so the rate of evaporation can be increased by increasing the temperature, right? So if we keep the temperature high, or let's suppose if we are talking about the sunny day, so temperature is already high over there. So the rate of evaporation will be greater, right? So rate of evaporation and the second factor, the surface area, right? Let's suppose if we are talking about the surface area. So let's suppose if we take the example of open container of an open container. Let's suppose if we are taking example of a 500 ml bottle. So you observe that the surface or the top mouth of that bottle is very much small, right? The area of that mouth is very much small. And if we compare that area with the area of bucket, or if the mouth of bucket, so bucket or the area of that bucket is much greater as compared to that bottle, right? So in which example the process will be greater of evaporation, in bottle or
Bucket?
bucket? So important is to know that what is the factor. So the factor is the surface area of the liquid. So if we increase the surface area, the surface area of the liquid is large, so it will provide space to more particles. A chance to escape from the surface. So increasing the surface area will also increase the rate of evaporation. And the third factor is related to a wind, right? If we are talking about the speed of the wind, so speed of the wind will also increase the rate of evaporation. So these are some common factor, and these application or these type of application we already encounter or observe in our daily life examples. So these are some common factors which depends or on which the evaporation depends. First one is the temperature. The greater the temperature, so higher will be the rate of evaporation. And if we talk about the surface area, so if we increase the surface area, so that will also increase the rate of evaporation. And if we increase the speed of the wind, that is natural process, we, or let's suppose if we place a fan, stand fan near the floor, so that will increase the speed of the fan, speed of the wind. So that will also increase the rate of evaporation, right?
Yes.
And we also say that evaporation is a cooling process. Evaporation is a cooling process. And how it is possible that evaporation is a cooling process? Let's suppose if we take the example of a swimming pool. So let's suppose when we are in swimming pool and after some time when we leave the swimming pool, so we feel a low temperature in our surrounding, right? We feel cold in, or we feel that surrounding is very much cold for us, right? And that's happening because when we leave the water surface, so the water molecules on our body start evaporating in the surrounding, right?
Yes.
Okay, so that is the example. So when we are leaving the swimming pool, so the water molecules on our body get some amount of thermal energy from surrounding, and due to increase in temperature, they start moving away from our body or from the surface of our body. So it means that the high temperature, or they consume the thermal heat of our body also, they gain some heat from surrounding and start moving away from the surface of the body, so that will decrease the temperature of our body. So in this way, the evaporation is a cooling process, right?
Yes.
That's why we say that evaporation is a cooling process because the particle of higher energy will leave the surface of a body, and in result, the temperature of the body will decrease because low energy molecules remains on the surface, right?
Yes.
So this is an other important factor that how evaporation work like a cooling process. So that also we can say that this is also a type of use in our daily life, but that is very natural and very common. So we don't have to set up additional experiment over there. This is natural process, right? So this is the concept of evaporation and boiling. And we also discuss the factors of evaporation because in this chapter, the most important topic is boiling and evaporation because there is a difference between them. And most people think that both are same or both works like same, but there is a great difference between evaporation and boiling. You observe the distance that how many factors are there, and boiling occurs at fixed temperature, but evaporation can be happen at any temperature, and it also works like a cooling process. Now we left out with a few topics in this chapter, which is melting, boiling, but we discuss about boiling. Now, most important is that we have to discuss about some melting process because we have to discuss the graph of melting process, and the other topic is related to latent heat of fusion. That is also very simple, and latent heat of vaporization. So these three topics are remaining in this chapter. And after that, we also done with this chapter. And the last chapter of thermal physics is related to thermal process. And we have to discuss about three process. And after that, we will complete the section of thermal physics also. Then we will solve the whole questions from the section of thermal physics, right?
Yes.
So next time we will complete the topic of that latent heat of fusion and evaporation. Then we will solve the question from these chapters. Then we will start the third chapter of thermal process, right?